Good morning students. Today let us learn how to derive Lensmaker's equation. To derive Lensmaker's equation, we will be using the real positive sign convention, and also we will be using the equation for refraction of light by spherical surfaces. Both these topics were covered in the previous lesson, and those who have not watched the previous lesson, its link is given in the description below. You may watch that. So let us go ahead and derive Lensmaker's equation. For that, let us consider a lens. What is a lens? It is a refracting medium enclosed by two spherical surfaces. So let me consider a convex lens. It has two spherical surfaces, and let me assume that this medium where it is which is enclosed by these spherical surfaces have a refractive index mu, and I suppose that outside this lens what we have is air. What is the refractive index of air? That is 1. So let me consider a principal axis for the lens which pass through the optic center O, and let me name this surface as S1 and the other surface as S2. And I suppose there is a point object P placed here. So P is the object, and let a ray of light be incident on the surface of this lens from this point object P. So this is the incident ray of light. Now when we look at the lens at this point, this will be the normal to the curved surface. So when a light ray enters from a rarer medium to a denser medium, what happens? It should bend a little bit towards the normal. So when it enters the lens, it will bend a little bit like this. So if there were no second surface, if we consider only the refraction at S1, it would have gone to a point Q prime. If there were no refraction at second surface, when we consider only the refraction at surface S1, it would have gone in this direction and the image would have formed at Q prime. But we know there is another surface here, so there will be a refraction taking place at this point also. What is the direction of the normal at that point? It is in this direction. The normal will be like this because this is a curved surface having radius of curvature somewhere here. So this will be the normal. So we know that when light ray enters from the denser medium of the lens to air, the rarer medium, it should bend away from the normal. So it will bend again, and due to refraction at this place, it will go and hit at this point. So if you consider a straight ray that passes through the along the principal axis passing through the optic center, it should go on straight. So these two rays will meet and you will get a real image at this point Q. So we consider the refraction taking place at two surfaces, one surface S1 and next surface S2. So what we are going to do now is we will take separately the refraction at S1 and refraction at S2 and use the equation for refraction of light ray by a spherical surface. We derived that in the last class. What is that? The general equation is mu1 by U plus mu2 by V is equal to mu2 minus mu1 divided by R. This is the general equation for refraction of light from a spherical medium, at a spherical medium surface. So here mu1 is the refractive index of the first medium, mu2 is the refractive index of the second medium, U is the distance of the object from the optical center, V is the distance of the image from the optical center, and R is the radius of curvature for the surface. So first let us apply this equation to refraction from surface 1. So first we are considering surface S1. So when you apply this equation, what is the first medium when it go and hit here? This is air. What is the refractive index of air? 1. So 1 by U. U is the object distance, that is from here to here, because P is the object. So this distance, suppose it is U. So we have it 1 by U plus, what is the second medium? It's the lens having refractive index mu. So instead of mu2, I am writing mu divided by. Now we are considering the refraction only at surface S1. So we assume that there is no surface here S2. So we will assume the situation where there is no second surface. So the light ray would have gone directly and reached the point Q prime. And the image will be formed at Q prime if refraction takes place only at surface S1. So we can consider this as the image and let V prime be the distance between the optic center and the image. Now, real positive sign convention, we will take the object distance as positive if it is on the side from where the light is incident on the surface. So, U is positive. And again, we will consider the image distance as positive if it is on the side where the light goes after refraction. So, here it's on this side where the light goes after refraction. So, V prime will be positive in this case. So, V prime equal to, now mu2 minus mu1, second medium is the lens. So, I have to take mu minus first medium is air. So, 1 divided by, let R1 represent the radius of curvature of this surface. So, I will consider it as R1. So, we got one equation here. Now, let us consider the application of this same general equation for refraction at surface S2. So, let me consider surface S2. So, when I consider surface S2, here is the refraction taking place. So, what is the first medium? The lens. So, here the first medium have refractive index mu and the second medium is air. So, the second medium will have refractive index 1. So, mu1 is the first medium. So, mu divided by, what is the object when light ray get refracted from here? See, the incident ray is in this direction. So, the incident ray appears to be in the direction of Q prime. It's not in the direction of P. So, it's not in the direction in which the light ray is coming from P. So, we cannot consider P as the object for this refraction. So, which is the object for this refraction? It will be Q prime. So, Q prime is a virtual object because for a person looking from here or at the refraction from here, the incident light ray is coming in a direction, in this direction. So, it appears that Q prime is the object. It is as if light is coming from here. So, here we have to consider the distance of Q prime from the optical center as the object distance. Now, it will be positive or negative. It is not in the direction, in the side from where the light is incident. For this refraction, light is incident from here, but the object is on the other side. So, we have to consider the object distance as minus V prime. Because by positive sign convention, the object distance can be considered positive only if it is on the side from which the light is incident. So, here this is the virtual object for the refraction at surface S2 and it's not on the side from which the light is incident. So I will consider here minus V prime as the object distance plus mu or mu2. Mu2 is the refractive index in the second medium. So here the second medium is air. Light is going to air. So I will consider it as 1. 1 divided by, this is the final image. So let us consider the distance between the optic center and Q, the final image, as V. So I will put this as V. And V is positive because it is on the side where the light ray goes after refraction. So 1 by V is equal to mu2 minus mu1. Mu2 second medium having refractive index 1 minus mu1 first medium is the length, so refractive index mu, divided by, let us take the radius of curvature for the second surface as R2. So R2. So this is equation 2. So we got equation 1 and 2. We can make the lens maker's equation by adding these two equations. So equation 1 plus equation 2. So when I add equation 1 and equation 2, I will get here 1 by u plus mu by v prime. There is a minus sign here, so I am going to put minus mu by v prime plus 1 by v equal to, we have here mu minus 1 by r1 plus 1 minus mu by r2. Okay, so here I have mu by v prime minus mu by v prime. So this get cancelled. And here if I consider this as negative, if I take this negative out of the bracket and put minus here, I can write this as mu minus 1. So this is minus of mu minus 1. So I will put here minus in the next step. So here I have cancelled these two because positive and negative, and here what I have done, I will take this as minus of mu minus 1. This 1 minus mu will be taken as minus of mu minus 1. So I get the equation 1 by u plus 1 by v is equal to mu minus 1. If I take common outside, it will be mu minus 1 times 1 by r1 minus 1 by r2. How we got the minus here? Because we have taken plus 1 minus mu as minus of mu minus 1. So there will be a minus sign here, that is this minus sign. So this is the equation we come up with. By now you will be knowing from general lens equation that 1 by u plus 1 by v is the focal length of the lens, or 1 by v plus 1 by v is the reciprocal of the focal length is 1 by f. So you know that from general equation 1 by u plus 1 by v is equal to 1 by f. That is equal to mu minus 1 times 1 by r1 minus 1 by r2. You can directly write like this, and this is the lens maker's equation. Or if you are not familiar with the equation that 1 by u plus 1 by v is equal to 1 by f, I can also show that by taking one particular case. Suppose the object is at infinity. So I have a small convex lens and this is the principal axis. Suppose this is the principal focus. So the distance between the optic center and the principal focus is the focal length of the lens. And suppose light is coming from a distant object. The object is at infinity. So the light rays coming from them will be parallel to each other. So a lot of light rays are coming parallel to each other. You know that the light rays which come parallel to the principal axis after refraction should go through the principal focus. sorry, it should go through the principal focus. This drawing is not clear. Let me rub this. We don't need this anymore. So I will draw a bigger figure here. So we have a convex lens, a principal axis. Suppose this is the principal focus, this is the optic center. So the focal length is the distance between the principal focus and the optic center, and light rays are coming parallel to the principal axis from a distant object, which means u tends to infinity. The object is at infinity. So the object distance is infinity, and we know that after refraction it should pass through the principal focus. So where is the image formed? The image is formed at the principal focus, which means the image distance will be f. So I will substitute the object distance as infinity and the image distance as f in this equation. So I will get 1 by infinity plus 1 by f is equal to mu minus 1 times 1 by r1 minus 1 by r2 from this equation. And we know that 1 by infinity is 0. So this will be 0. So we will end up with the equation 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. So this is the lens maker's equation. So you have to memorize this lens maker's equation, and also you should know how to derive the lens maker's equation. They may ask for 2 marks how to derive the lens maker's equation, and there will be numerical problems where you will have to use this equation. I hope it is clear to you. If there is any doubt regarding the derivation of this equation, please let me know. Now, I will also use this equation to find what will happen to the focal length of a lens when we keep it in water, glass, or some other medium other than air. So how the focal length will change when the lens is kept in a different medium. So here we consider the lens kept in air, right? So the refractive index mu here is the refractive index of the lens with respect to air. So I have 1 by f is equal to, in the situation which we consider, the light was entering from air to the lens. So mu will be refractive index of the lens with respect to air minus 1 into 1 by r1 minus 1 by r2. This is the focal length of the lens when it is kept in air. Suppose we keep the lens in water. So the refractive index of the lens in water will be 1 by f water. Focal length of the lens, if it is kept in water, will be equal to refractive index of the lens. The lens is made of glass. So let me express it as refractive index of glass with respect to water. So refractive index of glass with respect to water minus 1 times 1 by r1 minus 1 by r2. And we can express the refractive index of glass with respect to water as equal to refractive index of glass divided by refractive index of water. Again, we have derived this equation in the second lesson of the same chapter. If you haven't watched that, I will share its link also in the description below. Anyway, by substituting this in this equation, I can write that the focal length of the lens kept in water is equal to mu g by mu w, that is refractive index of glass divided by refractive index of water minus 1 into 1 by r1 minus 1 by r2. So, in order to find what change will happen to the focal length of a lens if it is kept in another medium, you have to consider equation like this. So, this is lens maker's equation. You have to memorize it. 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2, where f is the focal length of the lens, mu is the refractive index of the glass with which the lens is made, r1 is the radius of curvature of one surface, and r2 is the radius of curvature of the second surface. Now, this is the formula used by lens makers to determine what should be the radius of radius of curvatures of the two surfaces if they need a lens of a particular focal length. That is why it's called lens maker's equation. Thank you. I hope this is clear to you, and let me know if there are any doubts.